In this video, we will introduce the Women in Data Science Datathon and provide some hands-on tips for how to participate and even win this competition. In particular, we will go over example analysis and code for getting started with a competition. The Women in Data Science Datathon is a competition hosted on Kaggle where teams work with a dataset and build predictive models. This year's Datathon challenge is focused on a medical dataset of patients where the task is to predict whether a patient has been diagnosed with a particular type of diabetes called diabetes mellitus. Before you get started, we recommend to set up your compute environment and get the data. Here we will focus on how to perform exploratory data analysis and process the data for input to machine learning models. Exploratory data analysis is perhaps one of the most important steps in the data science pipeline, and that is because exploratory data analysis allows you to explore the features in your data, identify any patterns that might be useful for your prediction task, and identify any problems in your dataset, like missing data that need to be fixed before applying any machine learning models. Here, we can load the data using pandas package that is quite useful for manipulating the data. Just for starters, we might want to take a look at the first couple of rows of the dataset, see what kind of features are there. Here we already see that we have some numerical features like BMI, the body mass index. We also have categorical variables like ethnicity and hospital ID. These NaN values here also indicate that there's missing data, which make this whole task a little bit more complex. Finally, we can also take a look at the column that we're actually trying to predict, which is this last diabetes mellitus column. It's really important to understand what each of the columns means, so one could also take a look at the data dictionary, which provides a description of what the variables represent, and you can think about which variables might be relevant for our task of predicting the diabetes condition. So we can compute some basic properties like how many samples and how many columns do we have in the data, and take a look at the summary statistics like the mean, standard deviation, maximum, and the minimum for each column to note anything important or strange. So here, for example, the minimum age is 0, which already makes me wonder a little bit about what that means. Was that particular patient actually a newborn with an age of 0, or was just a 0 input into the patient's chart because the age was not known? So you can think about whether this is something that you might want to filter out or correct in your data later on. We also noted that there's some missing data here, so you can actually count how many entries there that are not missing. Now that we have understood the basics of the dataset, we can go further and try to visualize the data. This will help us to understand the features in the dataset more, whether we need to pre-process them, and most importantly, we can try to identify patterns in the data and formulate some hypotheses regarding what might be useful for our modeling down the line. Finally, in the real world, in industry or academia, it's really important to communicate the results of your analysis, so data visualization is really key for that. There are many ways to go about data visualization, so here, for starters, we can create this exploratory report through the pandas profiling package, which can tell us about each variable in the dataset, and it also plots the distribution of each variable. So here, for example, we can explore the body mass index variable, and here we can see that there are some missing entries for this variable, and also if we take a look at the distribution, for some reason there's a peak at the end around 70, so perhaps this variable was somehow capped at a maximum. So we could consider removing those samples or replacing them. Next, we can explore our target variable, diabetes mellitus, to see how many patients in the dataset have diabetes or not. This is important to know in order to understand the imbalance in the data. This will be important for modeling because if our dataset is very imbalanced, like it is here, if we just make a really silly model that always outputs a 0 for every patient, in other words, the model always says that the patient does not have diabetes without even looking at any of the other features, this type of model would already be about 80% accurate on this dataset because 80% of the samples indeed have the 0 or no diabetes label. Next, we can also explore which predictors are associated with our target variable. Those predictors will likely be critical for our task. So here, based on prior medical knowledge, we might think that diabetes is associated with high blood sugar. So we can explore that relationship by plotting the mean glucose levels for patients with and without diabetes. Here we can clearly see that patients with diabetes do have a higher maximum glucose level. So perhaps we should expect this variable to be a very important predictor of diabetes. In addition to the bar plot, we can also plot the distribution of the glucose levels. Next, we can also explore the predictors in our dataset. So these are all of the columns besides the diabetes indicator column. For example, we can explore the associations between our predictor variables. And this is important to do because it's possible that some of our predictors are highly correlated with each other. In that case, it might not make sense to have both of them because they essentially contain the same information. For numerical variables, we can make a scatter plot to explore their relationship. So here's an example of weight and BMI. Obviously, these two variables should be related since weight is used in calculation of BMI, and that's indeed what we see here. We can also make the same plot with our target variable highlighted. Finally, we can explore which variables are highly correlated with each other by computing the correlation between the variables and plotting these correlations as a heat map. So here we can observe that a lot of variables appear to be highly correlated with each other. And if we take a closer look, this makes sense because a lot of these variables actually correspond to the same measurement, but it's either the minimum or the maximum of that measurement. Now that we have explored the data a little bit, we can use what we have learned to pre-process the data. And once we have done that, we can use the pre-processed data for input to machine learning algorithms. The important concepts that we will discuss here are feature selection, encoding of categorical variables, scaling, as well as imputation of missing values. So feature selection and engineering is often really important for the success of your machine learning algorithms. So it's useful to think about perhaps based on some prior knowledge or intuition, how can you create new useful features or remove irrelevant ones? Here, for example, instead of relying on the provided BMI measurement, since that feature seemed to have some strange outliers and also contain missing values, we can actually calculate BMI ourselves. We know that BMI is just 10,000 times weight divided by height squared, and we can use that formula to make a new feature, this BMI calculated feature. So in addition, since in this dataset we have a lot of minimum and maximum measurements of variables during the first 24 hours of the patient's day in the ICU, we can also think about creating variables that measure fluctuation in these features. For example, here we created a variable measuring fluctuation in glucose. Finally, removing irrelevant features is also very important. First, we can remove features based on prior knowledge. So for example, the ID of the hospital or the ICU unit might not matter for predicting diabetes since these features don't really describe the patient's condition. We can also remove features that don't vary across the dataset. So if there's a feature that has some value for each patient in the dataset, that's not really helpful for prediction. And finally, features can also be removed if they have too many missing values or if they're collinear with other features. So here we can drop such irrelevant features from our data using pandas. So in real life, many measurements are not numerical. For example, we saw that the ethnicity variable in our dataset is text-valued, i.e. Caucasian, Hispanic, etc. So in order to apply machine learning models, which are functions, we need to convert categorical variables like ethnicity into numbers. So why can't we just assign numbers to each one of the categories? i.e., why can't we use 0 to represent Caucasian ethnicity, 1 to represent Hispanic, and 2 represent African American, and so on? So the problem with that is that numbers imply ordering. So this would imply that 1 Hispanic is greater than 0 Caucasian. And consequently, our machine learning models might not work because we're giving them this nonsensical ordering. So instead, we will encode these categorical variables as binary vectors. So for example, if our covariate takes on 5 different values, Caucasian, Hispanic, African American, Asian, and other, we would use a length 5 vector to represent this variable, where the first component of this vector represents Caucasian, the second component represents Hispanic, and so on. So now to represent, for example, the Hispanic ethnicity, we would put a 1 into the component corresponding to Hispanic and 0 everywhere else. This way of representing the data is called one-hot encoding, and it prevents us from having nonsensical orderings, since now we have these binary vectors and there is no natural order to them. So in Python, we can encode the data using, for example, this getDummies function from pandas. Now we will talk about scaling and normalizing the data. So most of the time, the features in the dataset have different units, such as pounds versus kilograms versus a completely different metric, like meters. This implies that features have different scales and ranges, and it turns out that many machine learning models are very sensitive to the scaling of features. For example, features with greater variability might have greater influence on the outcome. For example, consider this model which uses 10 nearest neighbors to decide whether a sample should be assigned to class 0 or class 1 based on two features, x1 and x2. Here we can see that x2 has a larger range, from around -10 to 50, while x1 occupies a smaller range, from around -1 to 1. Then, when we are trying to determine the nearest neighbors, only the distance in the direction of the larger covariate is going to count, and thus the model will essentially use only one feature, x2, and not x1, for making decisions. In order to avoid issues that arise due to different scales of predictors, we need to rescale the data. For example, we can rescale the data to fall within a certain range. That is, we transform every column in the dataset such that the points in that column fall within range of 0 to 1. Alternatively, we can also normalize our data such that each feature has 0 mean and unit variance. We can use functions from the sklearn library in Python to perform these transformations. Finally, as we have seen, sometimes the data that comes to us can be incomplete. In other words, that the data has some missing values. And in order to be able to use the data in machine learning models, we need to fill in the missing values, and this is what is known as imputation. So the easiest thing to do is when we have a missing value for a particular feature is to fill that missing value with a constant, such as the mean, median, or the mode of that feature. So for example, we can replace the missing albumin concentration values that we see here with the median albumin concentration of the observed values for that covariate. However, imputing missing values with a constant can be problematic because it can skew the distribution of the covariates. For example, here, when we imputed the albumin concentration with the median, it actually created a huge spike in the distribution of that feature. So this can lead our machine learning models astray to make wrong conclusions. A more sophisticated way to impute the data is using non-constant values, i.e. using models. For example, if we're trying to impute missing values of the albumin concentration, we can create a model that uses other columns in the dataset to predict the albumin concentration. So the model is trained on rows where we have no missing values for the albumin concentration column and other predictor columns. Next, for rows where we have missing albumin concentration values, but full information on our predictors, we can use our trained model to predict what the missing value should be. Another way to perform imputation is using k-nearest neighbors. For example, for each row with a missing value for a particular feature like albumin concentration, we can use other features with non-missing values to figure out what are the k-nearest neighbors of that row, and then just fill in the missing value by taking the average of only the k-nearest neighbors. So as a final note, one thing to keep in mind is that oftentimes, especially in medical data sets, the values are not missing at random. For example, if a patient is not suspected to have cancer, they would never get a biopsy, and therefore their biopsy results will be missing in the dataset. In that case, an additional variable that indicates whether biopsy results are missing or not would already strongly suggest whether that patient has cancer or not.